Hi guys, are you able to hear me? Are you able to see my screen? Are you able to hear me? Good morning everyone. I hope most of you guys have joined so that we can start as soon as possible. Please join the session. Let me check in my mobile how many people have joined. I think only 55 people have joined. These other people also join, and in the meantime, those of you who have joined this session, make sure that you like this video. Make sure that you have shared this video, shared this live session in each and every friend circle, in each and every group of yours, like Facebook, WhatsApp, Hike, Telegram. Everywhere you need to share this. And if you are coming to our channel for the first time, make sure you subscribe to this channel, because here we will be running complete courses for many subjects. Okay, 98 people have joined. Good morning, everyone. Gandham Mohan Rao, good morning. Gaurav Kumar, good morning. As soon as we reach this count of 150, then I'll start explaining. Okay, then we'll start our session. Sambhaji Bhosle, is all syllabus completed here or not? Sambhaji, we'll try to cover as many subjects as possible. My motive is to provide you free of cost multiple subjects, if possible all the syllabus. But once we have started a subject like power electronics, then I'll make sure that we cover this syllabus end to end. शिवानी, शिवानी क्लासेस हम लोगों की परसों से स्टार्ट हो गई थी. आज हमारा लेक्चर 3 है और अनअकैडमी प्लस पे कल से क्लास स्टार्ट करने का हम लोगों का प्लान है. Manisha, yes, you are at the correct time. You have arrived at the correct time. Ravi Teja, what about notes? Ravi, actually, whatever I am teaching in this session, I am keeping a PDF file with me. And soon what we'll do is, we'll create an Excel file in which we'll provide you the link to the video of each lecture and the link to the notes of each lecture. But that will be done within a week. So you need not worry about the notes. But what you need to make sure, whenever I am taking any session, you should have a pen and copy with you, so that if I give you a problem, you need to solve that problem by yourself. Okay. So even if you haven't brought copy and pen with you, make sure you get it before we start this session. Okay, and many people have joined with us, so I would like to tell you, first of all, welcome to this live session on power electronics. And since you have joined this session, make sure you like this video and make sure that you have shared this video with all your friends, with all your groups. The group may be in Facebook, the group may be in Telegram, the group may be in Hike. As well as, if you are visiting this channel for the first time, we are running a complete course on power electronics. We are running a complete course on electrical machines, as well as we are providing complete syllabus of random process and noise. So these three courses are running in parallel this month. If you subscribe to this channel and press the bell icon, you will get to know about all the notifications, all the videos that we are running. Okay, shall we start this session? Give me yes in the chat section and then we'll start this session. सत्यजीत, अनअकैडमी प्लस में कौन सा सब्जेक्ट स्टार्ट होगा? अनअकैडमी प्लस में कल इंजीनियरिंग मैथ्स और मशीन स्टार्ट होगा. Just tell me in the comment section yes, then we'll start the session. Okay, many students are saying yes, so we will start. So what I'll do is, initially, first of all, I would like to introduce to you our team of electrical EC and IN. Our team consists of me, Our team consists of me, that is Ankit Goyal. Okay. Then it consists of Vishal Soni sir. Vishal Soni sir is right now teaching random process and noise. Then it consists of Kamesh sir, who will be taking your EDC and analog. Then we have Ajay Gupta sir, who is also an expert in core subjects of electrical engineering. Okay. Then we have Shankar sir, who is an expert in network and digital electronics. Ramit sir, who is an expert in the instrumentation core subject. Rahul sir and Khemendra sir, who have launched SSC JE courses right now. Okay. So this is the team that I have built for you guys. This is a complete team of electrical EC and instrumentation, and this team will provide you many free of cost initiatives if you keep joining with us on our YouTube channel. If you stay with us on our YouTube channel, you will see many new initiatives starting, like quizzes, like question solving, like theory lectures. Many new things are coming your way. That is a personal promise from my end, but you need to make sure that you spread the. Yesterday what we did is we covered the concept of harmonics, right? We covered harmonics. Then I told you about Fourier series. I told you about two Fourier series. One was for the square wave. For the square wave, we saw the Fourier series was n equal to 135 up to infinity 4 Vs by n pi sine n omega naught t. Then we saw quasi square wave. The wave which is not completely a square wave is called as quasi square wave. We saw that the Fourier series was n equal to 135 up to infinity 4 Vs by n pi. Here was an extra term cos n alpha by 2 sine n omega naught t. Okay. So today I am seeing that only around 250 students are attending this session. I think many people are absent that attended yesterday. Make sure you inform those students as well that the session has started. Spread this word in your group, because not less than 300 attendance should be there. I want a minimum of 300 students attending every session. So make sure that you have spread the word. Make sure you have shared this among your group. Then what we started is, we started the concept of switches. Okay, here I talked about ideal switches. I told you about the properties of ideal switches, as well as I told you about practical switches. Okay, in practical switches, I told you that it requires a certain time to change the state from on state to off state and from off state to on state. Okay, it requires a certain time. We saw that when it is in the on state, it has a small voltage drop which leads to conduction loss. In the off state, there is a small current flowing through it which leads to clocking loss. That is, these switches are not lossless. Always a certain amount of energy is lost in operation of such kind of switches. Okay. One person is saying around 250 people joined, like only 50. Ramakant, only if the likes are only 50. I want you all to first go and like this video, and then we'll start the syllabus of today. Don't be hesitant in liking the video. Likes are only 38 if I see. Make sure that you have liked this video. Then we'll start today's lecture as well. Today we'll be learning some very interesting things, very new things that you haven't studied till now. Okay. And I also want you all to share this video. Please make sure you are sharing this video. Okay. So let us start. You guys remember what I taught yesterday? Is that clear to you all? Please tell me in the chat section, is that clear to you all? Do you remember? Is everyone clear about what we learned yesterday? Yes, maths will also start, but right now just focus on what I am teaching. Okay? Okay. Sajan, actually, I'll be sharing the notes. You need not take the notes. We'll be sharing the notes very soon. You need to visit our Telegram channel. There we are continuously sharing the notes. Just visit there and you can download the notes. Okay? Telegram channel is free for all. Hemant, switching loss is not equal to conduction plus blocking loss. It is a separate loss. Okay, then let me start the today's session. Okay, so what I'll do is first we'll learn about losses in switches. Okay, it is a very important topic from numerical point of view. We have to learn about what kind of losses are there in the switches. So as I have told you, losses are divided into three categories. First one is called as your conduction power loss. Okay, first one is your conduction power loss. Second one is your blocking power loss. And the third one, your switching power loss. Okay, we generally ignore this blocking power loss. We don't talk about this. It is very small. So we'll mainly focus on two things, that is the conduction power loss and the switching power loss. Is that clear? Okay. Telegram link, you can just visit the GATE aspirant group. You will see the Telegram link. पावर इलेक्ट्रॉनिक्स का पूरा सिलेबस करेंगे क्या सर? हाँ, पूरा सिलेबस कवर करने वाले हैं. ठीक है. So now we'll start first of all with this conduction power loss. Do you guys remember what is this conduction power loss? This conduction power loss I wrote as yesterday. It is the product of voltage across the switch and current through the switch when the switch is in the on state. Now what happens if we want to find out conduction power loss, if we want to find out what is the loss in the switch when it is in on state, then we'll have to model the switch. We'll have to model the switch. What is meant by this modeling? Modeling means we'll represent the switch as an electrical circuit so that we can apply the laws of network analysis and we can analyze its performance. Okay, modeling we study at many places. In electrical machine, what happens whenever you are studying equivalent circuit of any machine, that is also modeling. Why it is modeling? Because you are representing a machine just as an electrical circuit, so you are modeling it as an electrical circuit. Same thing I am telling, during the on state the switch has to be modeled in a certain manner and then we can talk about the losses in the switch. Okay, so it will always depend under which circumstances how the switch is modeled in order to find the loss. Okay, so I'll tell you about the models. The model number 1 of a switch is called as constant voltage drop model. In short, it can be written as CVD. Okay. In this constant voltage drop model, what happens when the switch is on? It is just represented as a voltage drop, or you can say just as a battery. If you represent the switch just as a battery, then it is called as the constant voltage drop. Okay. Basically guys, when I am teaching, just try and listen me rather than posting again and again different comments. We'll go through different subjects one by one. Right now we are running 3 subjects: communication system, power electronics and electrical machine. Just focus on that and then we'll see other subjects. Okay. See, in constant voltage drop model, what happens when we talk about on state? the switch will be modeled as a battery. Okay, this battery, suppose the voltage is V on and this is the current through the switch. Now where you have seen this CVD model, we generally observe this CVD model in case of power diode. In analog electronics also, in a diode, you say that during the on state, diode acts like a 0.7 volt voltage drop. Okay, if the diode is acting like a voltage drop, then it is basically nothing but a constant voltage drop model, and that is what I am saying. In CVD model, you just have to represent the switch as a battery. Okay. Yes, Siddharth, we'll learn power electronics in Hindi as well. But what I am telling, rather than focusing on what is going to come in the future, why not focus on what is being provided right now? Now, if we talk about the instantaneous power is nothing but product of voltage and current. Instantaneous power, nothing but product of voltage across the switch and current through the switch. The voltage is constant V on, the current may be variable. I don't know, this current may be sinusoidal, this current may be triangular, square wave, it may be constant as well. I don't know the nature of current, but what I am saying, during on state, we'll represent the switch as a battery. Dipanshu Rajput, Telegram link not working. For that you have to install Telegram. Now, when we talk about the average value of any function, how do we find average? We divide by the time period, then we integrate over a time period instantaneous power. Okay, that is how we find average of any function. Divide by the time period and integrate over one time period. Now if you do that, if you substitute, ESW is basically V on. Now since V on is constant, V on can be taken outside. So V on will come outside. What will remain inside? 1 by T integration over T ISW dt. Now if you see this function 1 by T integral over T ISW dt, that will be basically average of the current. Okay, that is the expression for average. So this is average of the current. So as you can see, the average power dissipation is nothing but voltage multiplied by the average of the current. Now many times I see a question from the student's perspective, sir, whether we should use RMS current for finding the power or we should use the average current for finding the power. Now in this expression, as you can see, since the voltage is constant, whenever the voltage is constant, we have to make use of the average of the current in order to find the power. Okay, we'll have to use the average current. Is it fine? So one point that I'll like to write here is, while finding power, this is a very important concept. While finding power, if one quantity is constant, one quantity means either voltage or current. If one quantity is constant, we use average of other quantity. Okay, so that is what you have to make sure you remember this. You need to learn this, that whenever one of the two quantities is constant, you always have to make use of average of the other quantity. So what we can say is, if voltage is constant, then it is voltage multiplied by average current, or if current is constant, then we have to multiply by average of voltage. Both these formulas are applicable, and this formula specifically you will see this will be used in case of rectifiers for highly inductive load. Okay, whenever either voltage or current is constant, you have to make use of average of the other quantity. Now let us move on to the second model of a switch, that is model number 2. Model number 2 is as a resistance. As a resistance means when the switch is in on state, then it will be represented as a resistance. It is generally used in case of a MOSFET. MOSFET in an on state is used as a or is represented as a resistance. Okay, MOSFET in on state. Piyush is asking why is it so we are taking average of the other. Piyush, I have just now derived. If you go by this derivation, the constant quantity will come outside the integration and the leftover integration will represent the average. As simple as that. When you are taking power, average of power, the constant quantity will come outside the integration. That is why. Okay. Is it fine? MOSFET will be represented as a resistance. Now here what we are doing is, in an on state, will represent the switch as a resistance. I'll call it as R on. This is ISW. Okay. The engineers group, why we use RMS current or voltage in resistance. I am coming to that. See, the voltage across this switch ESW will be ISW into R on. Now when I talk about the instantaneous power, always represent the instantaneous power by lowercase p. So this instantaneous power is product of voltage and current. If you substitute the value of voltage, it will be ISW square to R on. Now when we want to find out the average of power, how we will find out the average? It will be 1 by T integral over T dt. Now what I'll do is, I'll substitute the value of P is ISW square into R on to dt. Okay. So since R on is constant, I'll take R on outside. Okay. Is this fine? Now tell me, what is the formula for RMS of any function? RMS of a function is given by like this: 1 by T integration over T ft square dt. That is RMS. First take the square, then average, then root. That is RMS. If you see, this quantity is also same except square root is not there. If square root is not there, you can say that P average is nothing but I RMS square into R on. Is it now understood why we use RMS quantity in case of resistance? Because when we are taking the average, we are taking the average of a square. Average of a square is nothing but square of the RMS. Okay. For diode, we are representing as a battery. For MOSFET, we are representing as a resistance. Whenever it is a battery, we use average current. Whenever it is a resistance, we use RMS current. Ram Prasad Bagadi, why MOSFET is modeled as a resistance? When we'll learn MOSFET, right? When we'll understand MOSFET, that time I'll tell you. Whenever a channel is formed between source and drain, suppose it is a N-channel MOSFET. If a channel is formed between source and drain, it is a N-type channel. It is simply a N-type semiconductor. And any material will simply behave as a resistance. Okay. We'll study this when we'll study the MOSFET. That time I'll tell you. What is the difference between RMS, average and instantaneous? Samyuddin, if any function is a function of time, the value at any instant of time, suppose I say the value at 1 second, the value at 2 seconds, value at 3 seconds, these are all instantaneous value. Now average is nothing but sum of these values divided by the time. that is the average, and RMS, sum of the square of these values divided by time, and then we take the square root. So if you use only the value, it is instantaneous. Sum of the values by time, average. Sum of the squares divided by time, then taken square root is your RMS. MOSFET in off state. In off state, every switch will be modeled as open circuit. So you don't have to worry about the off state. We'll always model it as open circuit. John Cena, is current always DC in MOSFET? No, it is not necessary. Current can have any kind of waveform, but we are not going there right now, guys. Please focus on switches. I'm not yet going into the devices. We'll start the devices very soon. Then we'll talk about each and every device in detail. Is this point clear? Is this point clear? Just give me yes in the chat section. Is this point clear, where we have to use average current and where we have to use RMS current? Why in power electronics average values are taken? Hemant, see, what happens is that when we talk about energy, in electrical engineering, energy is most important factor. Then energy is nothing but integration of power, or you can say it is average power into time. That is why average power is very necessary when we talk about energy. Okay, so we shall move on. I'll ask you one question here. One question was asked, what is the shape of, just focus on this question, what is the shape of power versus current curve in a power MOSFET? You just need to tell what will be the shape of curve between power and current in case of MOSFET. This question was asked in ESE. Okay, just tell me in the chat section. Please tell me what will be the shape. Just one letter, one word you need to write the shape. What will be the curves like? What will be the shape of the curve? Okay, I am waiting for your comments. Ritika parabola, Ruchi parabola, Abhishek parabola, Rahul hyperbola, Adarsh hyperbola, Ashwant exponential, linear, hyperbolic, parabola. So the correct answer to this question is parabola. Why it is parabola? Just now I told you, in on state, the power in a MOSFET is nothing but I square into resistance. So if you now draw the curve between power and a current, if you draw the curve between power and current, it will be parabola. Okay, so the answer to this problem will be parabola. Okay, the answer to this question will be parabola. It will not be hyperbola. Is this fine? Now we will come to the model number 3. Model number 3 is called as piecewise linear model. Okay, that is called as PWL model. It is a PWL model. In this, what happens is, we'll represent the switch in on state by a battery as well as a resistance. Okay, E on, R on. This will be the current flowing through the switch, that is ISW. Now why it is called as piecewise linear? Because if you draw the curve between V and I, V means the total voltage. What is the total voltage in this case? The total voltage is V on plus ISW into R on. Just I have applied KVL. V on plus ISW into R on. So if you draw the curve between VSW and ISW, how will the curve look like? The curve will look something like this. So this curve is not completely linear. It is because it is not starting from origin. That is why it is called as piecewise linear. This model is clear. Now you need to know how we will write the power dissipation in this case. What will be the power? For a battery, I have told you the power is V on into I average. For resistance, we know the power is I RMS square into R on. Okay. So that will be the total power dissipation in case of PWL model. These are generally the three models that we make use in case of power electronics during on state of a switch. Are these models clear to you guys? These three models we generally use. Now what happens is, how do we decide which model is to be used? Generally SCR makes use of this PWL model. Okay. But in any examination, how will you decide which model you will be using? That will depend on what are the parameters given to you. If voltage is given, use CVD. If resistance is given, model as a resistance. If both are given, then PWL model. So whatever parameters are given for any particular device in any particular question, based on that you have to decide which model is to be used. Yeah, actually one correct thing one person is telling, this should not start from x-axis. Basically this curve should start from y-axis. It should be like this. Correct. That was a mistake. The slope should be r on. Should be like this. V on should be shown on the y-axis, not on the x-axis. Okay. Any other doubt about this? I'll be waiting for 30 seconds. You can tell me any doubts in this concept. This is all about the conduction loss that you need to know how to find the conduction loss in any device. For a model, actually what we'll do is the next class that I'll take about the switches, that will be completely based on problems. Okay, we'll talk about questions only in that class. Rama Prasad, I have told you why it is called as piecewise linear, because it is being modeled as y equal to mx plus c. If it was just y equal to mx, we'll call it as linear. Adarsh, capacitive model is for small signal analysis, that is not for power electronics. Aruna, basically we have modeled the switch as a straight line. In case of SCR, what is the curve in I and V? In case of SCR, the IV characteristics are something like this. Like this, right? So what we are doing is, we are modeling it as a straight line. We cannot use a non-linear curve, because in that case calculation will be very difficult. Okay, so that is why we are modeling it as a straight line. Is power only in average? I have told you why average power is necessary from the energy point of view, that I have already told you guys. Any other doubt? Okay. Piyush, I have told how to identify the model. That will depend on what parameters are given in the problem. If voltage is only given, use CVD. If resistance is only given, use resistance. If both are given, then PWL. Okay, I will not use right corner. That I just use to draw the curve between voltage and current. If they have all the parameters, then use PWL model, right? Moving on. Shatrudhan, we'll discuss about SCR in complete details. Right now, is power calculation clear to you all? Are you all clear about how to compute conduction losses? If that is so, I'll move on to the next kind of losses. Yandan, it is not the threshold voltage, it is the voltage drop in the on state. Because in SCR, threshold voltage is much higher than the voltage drop. Okay, so I'll start the next topic. The next loss that we will discuss, the switching power loss. So in the last lecture I told you the loss that occurs when a switch changes its state from on state to off state or from off state to on state, then the loss that occurs is called as the switching power loss. Okay, because when we talk about a practical switch, it always requires a certain time to change the state. It cannot change the state instantly. So the loss that is there during changing the state is called as the switching power loss. So let me first draw the voltage and current curve. Then we'll talk about this loss. Okay. This will be the curve when we talk about the voltage. And this will be the curve when we talk about current. Okay. Now, let me draw the voltage and the current curve. This is the voltage, initially it is high and the current initially is very low. Okay. Now when the voltage starts to increase, let me draw the markers in yellow. Okay. When the switch starts to turn on, the voltage will decrease. Okay. And at the same time, the current should increase. At the same time, this current must increase. Now the switch has turned on, the current will stay high and the voltage will stay low. Now when you want to turn off the switch, the voltage should again start to increase and the current should again start to decrease. Okay, so I'll draw current as well. Current will again start to decrease. Then it will remain constant at a low value during off state. It will remain constant at a high value. Is this curve clear? How I have drawn this curve? Here what I have done is I have shown you that this state is basically the off state of the switch, in which case the voltage is high and current is low. This is your on state, this is your again off state. And the time taken to go from off state to on state is called as T on. And the time taken to go from on state to off state is off. Okay. This I'll call as suppose V and this I'll call as I. Okay. Ignore this. Consider this to be approximately 0. Consider this also to be approximately 0. So that is I am ignoring voltage drop during on state, voltage drop during on state, and leakage current during off state. This all I am ignoring. Is it fine? What I am ignoring is fine. Okay. Reverse recovery we are not talking about right now. Just tell me, is this curve clear to you guys? Deepak, actually increase and decrease are not linear, but then again we are approximating them as linear. in order to simplify the calculation. Okay, just in order to simplify the calculation, we are taking them as linear. Prasanna, it is not actually 0, we are just taking it as 0. This curve is clear or not? Okay. Then our objective basically is to find the power loss during this interval of T on and T off. We need to find the power loss. So what I'll do is, I'll take this instant as T equal to 0 and this as T equal to T on. First of all, remember, just by shifting the curve, area under the curve will not change. That is why while computing the power, you can choose any instant as T equal to 0. That is your choice. It is not necessary where the curve starts. You can choose any instant as 0. So I'll write here also, while finding power, we can choose any instant as T equal to 0. Is it fine? Now, what I'll do is, in order to find the instantaneous power loss, how do we find instantaneous power loss? Instantaneous power is nothing but product of voltage and the current. It is the product of voltage and the current. Now, in order to find this product, we need to know the equation of voltage and the equation of current. Why we need to know the equation? Because during T on as well as T off, the current and the voltage are variable. They are not constant, right? Once anything is variable with respect to time, you need to know the equation with respect to time. How to write the equation? See, for decreasing curve, use this equation. Maximum value 1 minus T by 1. This is basically your interval of decrease. For increasing curve, what you have to do, just use like T by T. The terms are same, maximum value and the interval. Okay. Ravindra, this class is in English. Later on, after a few months, I might be teaching the same topic in Hindi, but right now I'll conduct this in English. Is this fine? This you need to memorize. These both equations you need to memorize, and it is very easy. When you start solving numericals based on this, then it will not be very difficult to memorize this equation. Okay. Now what I'll do is, I'll remove this. I'll take one by one each interval. Okay, I'll take one by one each interval, first during T on and then again during T off. You have to go interval by interval. Okay. Ravindra is asking, if V and I are variable, then can we find P average? Yes, we'll be able to find P average. First of all, first interval that I am choosing is from 0 up to T on. Okay. When I am talking about 0 up to T on, what I'll say is, the voltage is a decreasing curve. So how you will write the voltage? V into 1 minus T by T on. and the current is an increasing curve. So how you will write? Current will be maximum value by interval, means the interval in which the voltage decreases and the current increases. Okay. So now when you find out the power across the switch, ESW, ISW, it will be V into I by T on E minus T square by T on. What I have just now done is multiplied voltage and current. But this is your instantaneous power. Okay. Now if you want to find out energy, how do we find out energy? Please don't say it is power into time. Okay. That is one of the most common mistake that every student makes, that energy is power into time. Do you know that it is not actually true? If you are an electrical engineer, what you must think, that energy is nothing but integration of power. Because it is not necessary that the power is constant. Like here you see power is a function of time. Whenever any quantity is a function of time, we will not directly multiply time, we will take the integration. So it will become Vi by T on. We will integrate from 0 up to T on. E minus T square by T on. Is this point clear? Rishabh is saying integral of average power. No, integral of instantaneous power. Energy is always integration of instantaneous power and not average power. What you can say, energy is integration of instantaneous power, or it can also be written as average power into. Now, you can directly integrate this, right? So I'll write down the integration. It will come EI by 6 into, if you simplify this, this will be the energy during the on state, EI by 6 into T on. Next, let us find out the same way energy during T off. During T off, how you will write the voltage? What I'll do now is, I'll take this time as T equal to 0. Now this will be T equal to T off. You can always shift the origin in order to write the equation. Now the voltage is now an increasing curve. If the voltage is increasing curve, you can write V into T by T off. And as you can see, current is a decreasing curve. So you will write I 1 minus T by T off. This is during the interval from 0 up to T off. Now what is the average, what is the instantaneous power? It is the product of voltage across the switch and current through the switch, Vi by T off into T minus T square by T off. Okay. Again we need to find the energy during off state. So what I'll do, I'll integrate this power from 0 up to T off. So what you will take, Vi by T off will come outside. Integration from 0 up to T off. T minus T square by T off. If you simplify, you will get Vi T off by. You don't remember these expressions, okay? You need not remember these expressions. You just need to understand how I am finding it. Okay. Now what we'll do is, if I talk about energy loss during switching, energy lost during switching, it is nothing but E on plus E off. That is Vi by 6 T on plus T off. Now if you want to find out average power, it is nothing but energy by time period. 1 by time period is nothing but frequency. So it will be VIF by 6 T on plus T. Now don't say sir the time period is T on plus T off. No. If you go back, this is the entire time period. Time period is the time after which a graph repeats itself. So this is the entire time period. It is not just T on plus T off. Okay. The minimum value of time period is actually T on plus T off. In the last class also I told you for maximum frequency we use the time period as T on plus T off. But the actual time period is more than T on plus T off. So while finding the average, you will divide by the total time period, that is you will multiply by the frequency. Now what you need to remember about switching power loss, write equation for V and I during T on and T off. Then multiply both equation, find instantaneous power, then integrate instantaneous power to find energy. Okay, energy during switching, nothing but energy during on state plus energy during off, and average switching loss, nothing but switching energy by time, or you can say frequency multiplied by switching energy. You don't remember the formula for switching power loss, you remember these steps because the waveform might actually change during an actual examination, and that is why you won't be able to use these expressions. You just need to understand the method that I have used in order to find the switching power loss, so that no matter what waveform comes in the examination, you will always be able to find the correct answer. Is this switching power loss clear? Rajesh, why from 0 to T off? I have already told you can take the origin anywhere, but the equations that I have told you, the equations for voltage and current that I have told you, they are only applicable if the curve starts from 0. The equation that I have told you like this is only applicable if the curve starts from 0. Curve starts from t equal to 0. Okay. Is everyone clear about the switching power loss? So basically, what kind of question can be asked from this topic in any examination, like even gate examination? 1 mark question they can ask you to find conduction power loss, and even switching power loss can also be asked for 1 mark. But that you need to know. In conduction power loss, you can directly find using average and RMS current. In switching power loss, you need to write the equation of voltage and current. So that is all about the losses in the switches. Blocking power loss, we ignore the blocking power loss. Why take total time? Because while finding the average, we always have to take the total time period. That is the basic formula for average. Okay. Now, what we'll do now is, we'll understand the new topic called as classification of switches. Okay, we'll understand how to classify the switches in different categories. John Cena, what is hard switching and soft switching? Hard switching is when hard switching is called as when the transition time is very low, and soft switching when the transition time is large. That is, the voltage graph falls slowly during soft switching. It falls rapidly during soft switching. Okay, this chapter is very important from ESE point of view as well. Now, first of all, we'll talk about classification based on control action. Control action means whether or not you are able to control the switching. Okay. So the first is called as uncontrolled switch. Now what is this uncontrolled switch? See, when I introduced power electronics, I told you every switch must have three terminals, one for input, one for output, and one for turning the switch on or off. Okay, it requires three terminals. Now what is an uncontrolled switch which does not have a third terminal? That is, you cannot control the switching of the device. You cannot decide when it will turn on and when it will turn off. Okay. So what is it? Turn on and turn off. Turn on and turn off cannot be controlled. Cannot be controlled. Turn on and turn off cannot be controlled. That is called as your uncontrolled switch. What is the example? The example is simply a diode. Why a diode is called as uncontrolled switch? Because when the diode is forward biased, it is on, and when it is reverse biased, it is off. That is, there is no third terminal. There is no third terminal that decides switching of the device. Okay. That is why it is called as a uncontrolled switch. Is it clear? Second, we'll talk about semi-controlled switch. Semi-controlled switch is when we have one state under our control, but the other state cannot be controlled. That is, only one state can be controlled and not the other. And not other. That is, you can either turn the switch on or you can turn the switch off, but the other thing is not in your control. You cannot control it. That is like you can turn the switch on at your own will, at your own wish, but you cannot turn it off by yourself. The best example of such a switch is SCR. In a SCR, what happens? It can be turned on by positive gate pulse. It cannot be turned off. Via gate pulse. Okay. It can be turned on via gate pulse, but it cannot be turned off via gate pulse. The difference between power diode and diode we'll see later on when we study power diode. I'll clearly explain the difference. Third one is called as controlled switch, or you can say fully controlled switch. Okay, or you can say it's a fully controlled switch. As you might have understood by now, fully controlled switch will be when both states can be controlled. That is, you can turn the switch on by yourself, you can turn the switch off by yourself. The best example is transistor family. What is transistor family? Power BJT, IGBT and MOSFET, GTO, triac. All these are devices which are fully controlled switches. So that is the first classification that we study. It is very basic. It should be clear to all. The next classification is important. It is basically based on conduction and blocking. Conduction and blocking. Now, first of all, in this classification, we first talk about unipolar switch. What is a unipolar switch? It blocks one polarity of voltage. What is meant by blocking the voltage? Blocking the voltage means even if you apply the voltage across the device, it will not turn on, it will stay off. That is called as blocking the voltage. Blocking means off state, right? That I have already told you. So blocking the voltage means when it does not turn on even after applying a certain voltage, it stays off. So what does it mean is, if we draw on a IV curve, suppose it can block positive voltage. Okay, we'll show a curve like this. You can either mark a cross or you can show like this. It is your choice. What does it mean is, this is the maximum voltage that it can block. The cross point represents maximum voltage. This solid line represents current is 0. That is, we are taking the assumption of an ideal switch kind of thing. Ideal switch here means that current is 0 during blocking state. Are you getting my point? It can block up to a certain maximum value, after which the switch will break down. What is the example of such kind of characteristic? The example is BJT, MOSFET, IGBT. They all block the positive voltage. That is, they will stay off even if positive voltage is applied. Kudhir, active and passive switch. Padiyar Krunal, active and passive switch are nothing but active switch which has a third terminal, passive switch which does not have a third terminal. So diode will be a passive switch. Similarly, what can be the other condition? The other condition in unipolar switch can be when it blocks a negative voltage, right? When it blocks a negative voltage like this. Either you can show this solid line or you can show the cross. You need not show both. So that is the maximum voltage that it blocks. Beyond this voltage, the switch will break down. So this is the best example is diode. Diode can block or diode stays off for negative voltages up to the breakdown voltage. After a certain value, the switch will start to conduct. So that is why this is called as unipolar. Similarly, the other kind of switch will be called as bipolar switch. Now, what is bipolar switch? As you might be understanding from the name itself, it blocks both polarity of voltages. It blocks both polarity of voltages. That is, if we draw the curve, then what you can show is, you can show two crosses. Or you can show a solid line like this. It can block positive as well as negative voltage. So what are the example of such a device? SCR, ETO, triac. Okay. These are the switches which are able to block both polarity of voltages. Okay. Next. Now the next thing will be based on conduction. So I'll say first is unidirectional switch. Right now the two classification that we saw were based on the blocking voltage. Now we'll discuss about conducting current. Unidirectional is conducts current in only one direction. In only one direction. That is, and when you take an ideal switch in this case, when you talk about an ideal switch, what you will say? You can say that during on state the voltage will be 0. So when we draw on an IV curve, it show like this. That is, it is only able to conduct one current. And why we are showing on y-axis? Because we are assuming that during conduction the voltage is 0. If the voltage is 0, that means it is on the y-axis. Okay. One question is coming, why switching losses are present in a practical switch? Because it takes a certain time to change the state. During that, voltage and current both will be non-zero. What are the examples of such kind of switch? I'll write SCR, PTO, power BJT, power MOSFET, then other than that diode. All these are the unidirectional switches. Now what about the other alternative? The other alternative is bidirectional switch. Actually there is one mistake here. Power MOSFET is actually bidirectional. It is not unidirectional. Here we must write IGB. Okay. Now in case of bidirectional, as from the name itself is clear, it conducts current in both direction. Both direction means from positive to negative terminal as well as from negative to positive terminal. Okay. So how you will show that? You will show like this. Between two values, the curve will be going on. What are the examples? The examples are diac, triac, power MOS. Okay, so that is another classification that we do for the case of switches. Is this very clear to you? Okay. Charu column IGBT is not bidirectional, it is unidirectional. Here the crosses represent, see, this is the maximum current. Here this is the maximum current and this is the minimum possible current. Ravi Teja, actually SCR is bipolar and unidirectional. That will come to just now. Manish Kumar, that depends on the switch. Which switch is being used in what application? Like for fans, we have AC voltage controller. There we make use of triac, which is bidirectional and bipolar. Yes, RCT is bidirectional. Bhavya, you are right. Yes, Ritika, RCT is bidirectional. So I'll add here RCT. दीपांशु, that I'll tell later on unipolar bipolar को majority minority carrier से कैसे relate करते हैं. That will come to definitely later on. Ram Keshav, bipolar means conduction due to both electrons and holes. Yes, that is also true, but that is called as bipolar device, not a bipolar switch. Okay, so we will move on. Now what we'll discuss is ideal characteristics of switches. Okay, ideal characteristics of switches. So first I am talking about power diode. In case of power diode, we show the diode like this. This is anode, this is cathode. This is the voltage across the diode. This is the current across the diode. Now, as I have told you, power diode, if we draw the ideal IV characteristic, how will they come out to be? It can carry unidirectional current and it can block unipolar voltage. Okay, that means it is unidirectional and unipolar. Is unipolar and unidirectional. And based on first classification, I told you that it is an example of uncontrolled switch. And based on its characteristic, you can see in which quadrant it is operating. That is the safe operating area is second quadrant. Based on the ideal characteristic, you can say safe operating area is second quadrant. Then we move on to the next switch. For the next switch, we will call BJT, that is bipolar junction transistor. How do we draw BJT? This is collector, this is base, and this is emitter. Now I told you BJT conducts in only one direction, as well as it can only block one polarity of voltage like this. Okay, so it is an example of a fully controlled switch. We studied that the entire transistor family fully controlled. Again, it is unipolar and unidirectional. Unipolar and unidirectional. Based on this curve, as you can see, the safe operating area is your first quadrant. Okay. Then moving on to the third switch. The third switch that we'll take is power MOSFET. Now power MOSFET has an inbuilt body diode. What is an inbuilt body diode? When we'll study the structure of MOSFET, there I'll show you how we have an inbuilt diode. What are the terminal? Gate, source, or you can say gate. The upper terminal is generally kept as drain. This is your integral body diode, or you can say internal body diode. That is, this diode is present inside the body of a MOSFET. You cannot change the structure. This diode is internally inbuilt. Praveen is saying BJT is a bipolar device. Praveen, you are absolutely correct. BJT is a bipolar device, but I am not using the word device here. I am using the word switch. Being a bipolar switch means blocking both the voltage. Being a bipolar device means conduction due to electron and holes. So bipolar, check the next word as well. If it is a switch, talk about voltage. If it is a device, talk about charge carriers. Is this point clear? BJT, when we'll study, then we'll talk about blocking and everything. Just right now, you have to remember these ideal characteristics. I'll explain you the structure and working of each and every device. Then I'll tell you how it blocks each and every voltage. Now, when we talk about the characteristic, of a power MOSFET, It is bidirectional and it is unipolar. So it is, first of all, due to being a transistor, it is a fully controlled switch. It is a fully controlled switch. It is bidirectional and unipolar. Bidirectional and unipolar. And as you can see from the graph, the safe operating area is first and fourth quadrant. Okay. Next switch. Next, I like to discuss IGBT. We'll complete transistor family here. It is a combination of BJT and MOSFET. This is gate, this is collector, and this is emitter. Okay. Now, in case of IGBT, as I have told, it is unidirectional and it is unipolar. Okay. So it is a fully controlled switch. It is unidirectional and unipolar, and SOA is same as BJT. Okay, you don't need to understand how to recognize this, you just need to remember this. Okay, for ideal switches, diode operate in first quadrant safely. Na Aparna, you are right, but based on this ideal characteristic, we see that the safe operating area is second quadrant. What is the purpose of inbuilt diode, Ritika? There is no such purpose. It is not intentionally kept. It is induced inside a MOSFET that I will show you based on its structure. IGBT does not have a body diode, Praveen. It has a transistor inside it. Okay, or you can say it has a SCR inside it, but it does not have a diode. Rishikesh, because we can turn on and turn off the MOSFET by just adding or removing the gate signal. That is why it is fully controlled. Okay, it is not based on that body diode. If you want to turn on the MOSFET, you just apply the gate voltage. If you want to turn it off, remove the gate voltage. Next is your SCR, that is silicon controlled rectifier. This is your gate terminal, this is anode, this is cathode. And what we have studied about the characteristic of a SCR. In case of characteristics, we have seen that SCR is bipolar and SCR is unidirectional. I told you it is a semi-controlled switch. That is, you can turn it on but you cannot turn it off. Then it is bipolar and unidirectional. And SOA, as you can see from the curve, it is first and second quadrant. Okay. The next device that we'll talk about is GTO. GTO also belongs to the thyristor family. It is a modified version of SCR. Just show a cut here. Anode, cathode and gate. It also has the same ideal characteristic as those of a SCR. So it is also bipolar and unidirectional, but what is the difference? GTO can be turned off, that is why it is fully controlled switch. It is a fully controlled switch. It is again bipolar and unidirectional. And SOA is again same as that of SCR, first and second quadrant. Last device that we'll discuss is your triac. Triac, how is it shown? Triac, we write here MT1, MT2 and gate. Now as I have told, triac is a bipolar and bidirectional kind of switch. Okay, so that is IV. So it is first of all fully controlled switch. Then it is bipolar and bidirectional. And SOA, all four quadrant. Okay. Gaurav Sharma, actually I am just taking based on the current and the voltage intercept because the characteristics are like this. That is how I am telling. Okay. MT1 means main terminal 1 and MT2 means main terminal 2. There are no anode and cathode. There is only main terminal. RCT is basically bidirectional and unipolar switch. RCT, if you want to know RCT, it is bidirectional and unipolar. Okay. Those of you who want to know the Telegram link, the Telegram channel, that is free for everyone, that is given in the video description. SOA का significance, for SOA we know which operating points are safe. If you view the last lecture, Ruchi, I have told exclusively about SOA, why SOA is important and what is the practical application. Up to here is clear to everyone? Is everyone clear about what we have discussed? Random SOA is the safe operating area, that is the set of voltage and current at which the switch can operate. Aparna, triac is a fully controlled switch. Practical characteristic, Akhilesh, we will cover when we talk about each and every device. Harshvardhan, yes, you can say it is kind of MOSFET. Okay. Now one more thing that we learn here is, I'll talk about composite switches. Composite switches. What is this composite switches is when two switches are connected together. Understand this thing, this is very unique that I am going to tell you here. You might not have heard it earlier. Okay. Kushal, diac is not important, that is why I have left it. Random RCT we will study separately. No need to over focus on that. First, let us talk about composite switches when two switches are connected together. So the case 1 is basically your series connection. When two switches are connected in series. Suppose let us take an example of a BJT connected in series with a diode. Okay. That is the voltage, this is the current. Now we need to know the characteristics of such kind of switches when two switches are connected in series. In series, what happens is, what is the condition for series connection? That in series, the current is same across all the devices. So what I'll say is, I'll say that you draw the characteristic of both the switches. For BJT, how is the characteristic looking like? Is like this. I versus V. Similarly, draw the characteristic for a diode. For a diode, how is the characteristic? Is like this. In series connection, the current must be same from both the devices and voltages are added by KVL. That is why what I say is, take intersection of current. Since the current is same, take intersection of current and voltages are added. So union of voltage. What do I mean by this statement is, when you draw the characteristic of the composite switch, take the common part of current. Common part is, this is positive, this is positive. So common part is this positive. Union of two sets. Suppose I say 1, 2, union 2, 3. That is, take all the elements like 1, 2, 3. So positive and negative union is common. Okay, that is, both the points will come, and that will be the characteristic of this BJT connected in series with the diode. Alok Pandit, if SCR is on, why don't we turn it off? Alok, we'll discuss SCR in much detail. This is all about switches. This is not about the devices. Try and understand. First thing, we are studying the switches here. We are not studying the devices. We are not going inside the device, how a device is particularly constructed. Yes, we get unidirectional and bipolar. Correct, Rajesh Adepu. Samyuddin, switching losses are not present in an ideal switch. Next, we'll take second case, case number 2, that is parallel switches. Okay, so let me draw a circuit. Suppose this is a switch where a diode is connected across a BJT. Okay. Now in parallel connection, what is the condition? That voltage must be same and current is added by KCL. So what I'll do is, I'll draw the characteristic of individual devices first of all. For BJT, how will be the characteristic? Will be like this. But if you see that diode is connected in reverse configuration, one most important point you have to remember, that diode is connected opposite to BJT. If the diode is reversed, then what you have to do, you don't draw the normal characteristic of a diode, you reverse the diode. Reversing the diode means reverse the current and voltage. Diode carries positive current, reverse means negative current. Diode blocks negative voltage, reverse means positive voltage. This is BJT. This is reversed diode. Okay. It should have positive current, but due to reversal I am taking negative current. It should have negative voltage, but due to reversal I am taking positive voltage. Now since the voltage is same, we will take intersection of voltage. Since current is being added by KCL, we will take union of current. Okay, once I have told you this much, can you draw the characteristic of the composite switch? Can you draw? Okay. So if you take intersection, you have to take common part of voltage. Common part is positive. If you take union of current, you have to take both the currents, positive as well as negative. So that is the characteristic of the composite switch. Okay. Riju, does controllability affect in this connection? No, Riju, controllability is not affected. Okay. Yeah, many people are correct. Bidirectional and unipolar. That is the correct answer to this kind of problem. So what I have told you is when you connect multiple switches together, then how you find out the characteristics of such a composite switch, you have to remember this method in order to solve the problems in examination like gate. Okay. So we'll wind up here. First of all, before ending this video, what I like to tell you is, if you want to learn in a more personalized manner, more personalized is when I can give personal attention to each and every student. I can answer each and every query of yours. You have to join Unacademy, where we conduct live classes on a daily basis.